Hello, my name is Kylie Wilkins and welcome to my makeshift classroom. Today I'm going to be teaching you about Lewis structures and molecular geometries. So first we're going to start with carbonyl dichloride. So in order to start, we are going to count our valence electrons. And in order to do this, we are going to look at each element and their valence electrons. So chlorine has 7 valence electrons, and since there are 2 chlorines, we need to multiply by 2. Okay, now we need to add in how many valence electrons carbon has, and carbon has 4, and oxygen has 6. So we are going to get a total of 10, 14, 24 valence electrons. 24 valence electrons. So now that we know how many valence electrons we have, we are going to start building our molecule. So in order to start building our molecule, we are going to find the most unique element in our molecule. And so this is kind of a unique example because there are 3 different atoms being used. So in order to find our central atom, we're going to use carbon, because carbon, if you see carbon in a molecule, that is most likely the central atom. So we're going to use carbon as our central atom. So we're going to just draw carbon. Now we are going to completely fill with our 3 other atoms. So I like to go kind of in a circle, but people like to fill them differently, but this is just how I'm going to fill it. So I like to start with bonds. So 1, 2, 3, because there are 3 elements, so there should be 3 bonds. Then I'm going to fill it, so oxygen, chlorine, and chlorine. So this is what I started with. Now I'm going to completely fill my diagram with valence electrons. So that means chlorine's gonna get 3 sets of lone pairs. Oxygen's gonna get 3 sets of lone pairs. And the other chlorine is going to get 3 sets of lone pairs. Just like this. We're going to completely fill our diagram. And now we're going to count our valence electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 17, 18, 19, 20, 21, 22, 23, 24. So you might think, hey, we are done. We have 24 valence electrons, we can stop. That's perfect. But carbon isn't satisfied with its bonds. Carbon needs 4 bonds, as well as oxygen. Oxygen needs 2 bonds. So in order to satisfy this, we are going to make this bond a double bond. But now something isn't right. Now we have 26 valence electrons. So to fix this, we are going to get rid of one of the lone pairs on oxygen. Now we could probably keep it like this, but the correct way to write the lone pairs is like this. The bonds are going to want to be equidistant. Well, not equidistant, but they're going to want to equally distribute, so that's why they need to move like this. Okay, now that we have our Lewis structure, we are going to check formal charges. Formal charges should be 0 for this molecule because, as you can see, this does not have any charge. So to calculate formal charge equals formal charge is the number of valence electrons, so number valence electrons minus the number of non-bonding electrons plus the number of bonding electrons, so number of bonds. So we are going to start with the easy example, and we are going to start with the 2 chlorines because the 2 chlorines look the same. We only need to do 1 formal charge for it. So we're going to write Cl. I just like to label all of my formal charges. Then I'm going to go dot, dot. Now I'm going to take the number of valence. So Chlorine has 7 valence electrons. 7 minus the non-bonding, so the lone pairs, there are 6. So minus 6 plus the number of bonds. There's 1 bond, so we're going to add 1. And then this would be 7, so 7 minus 7 equals 0. Meaning that the chlorine has no charge. So next we're going to do carbon. Carbon has 4 valence electrons. Now we're going to subtract it from the non-bonding. That would be 0. Carbon has, all of carbon's electrons are currently being bonded. So next we are going to add in the number of bonds. There are 1, 2, 3, 4 bonds, so 4. And 4 minus 4 equals 0, so carbon does not have a charge. So the formal charge of carbon and chlorine are both 0. Let's double check our oxygen though. We want to make sure we are covered across the board. So oxygen has 6 valence electrons. And now we're going to subtract the number of non-bonding. It has 4 non-bonding electrons, and we are going to add the number of bonds. There are 1, 2 bonds here, so that would be 2. And then we have 6 minus 6, which is 0. So the formal charge for this atom, for this molecule, is 0. Okay, now we are going to look at molecular geometries for this molecule. So I'm just going to get rid of formal charge. So if you want to copy it down or you want to look at it, there it is. I'm just going to get rid of it so I can draw my correct structure. So in chemistry, this looks great, but this is not how things exist in nature. The goal of a molecule is to kind of like balance everything. So it wants everything to be like equal and together. So what we're going to do is we are going to find the molecular geometry for this. And how we do that is we have to count the electron domains. So to count electron domains, you must count lone pairs and atoms. So this is the central atom, so you need to work with the central atom. So there is 1, 2, 3 electron domains. There would be 4 if there were 2 dots down here on that. But carbon currently is satisfied with all its bond, so it has 3 electron domains. ED stands for electron domains. So in order to find the electron domain geometry, you need to know how many electron domains there are. So when there are 3 electron domains, the electron domain geometry is called trigonal planar. Now sometimes the electron domain geometry and the molecular geometry are 2 different names. But for this one, they are the same because there are no lone pairs to mess us up in this example. So now in order to draw a trigonal planar, we need to know what that looks like. So a trigonal planar has 120-degree angles between all of the outside atoms. So in order to draw this, I like to start with my carbon. There is my carbon. Then I like to do 1, 2, 3. This is what a trigonal planar looks like. I think it kind of looks like a fidget spinner, if you know what that is. So I like to just start like this. Like, no matter what I'm doing, if it's a trigonal planar, I always like to put the central atom in the middle and put the 3 lines around it, because that's the shape I'm looking for. Okay, so now we are going to fill it with our outside atoms, which are 2 chlorines and an oxygen. So here's my oxygen, my chlorine 1, and my chlorine 2. Now that I currently have all 3 of my outside atoms, I'm going to fill my valence electrons. But I want to remember that this oxygen has the double bond. So I'm going to draw in the double bond before I forget. And now I'm going to fill all of my electron. now that that is done, all that is left for me to do is draw in the bond angles. The bond angles are 120. These are all on a same plane. They can lie flat on a piece of paper. They will be flat on a piece of paper. There's no 3D. It's two-dimensional. Yeah, so this is how you do the first example, and now we will move on to the next one. Okay, so next we have aluminum chloride. So aluminum chloride looks like this. Sorry, just give me 1 second. I didn't dry it enough. Okay, so it looks like AlCl3. So AlCl3. So we are going to start by counting the valence electrons again. So in order to do this, we need to know how many valence electrons aluminum has. Aluminum has 3 valence electrons. You can find this out from the periodic table. And now we are going to add on the amount of chlorine valence electrons. So in order to do this, we are going to take 7, because chlorine has 7 valence electrons, and we are going to multiply it by 3, because there are 3 chlorines. So 7 times 3. Now we are going to add these together. So 7 times 3 is 21, plus 3 is 24 valence electrons. So much like the other example with the same amount of valence electrons. So next we are going to look at the central atom. So the central atom is aluminum. So we are going to take aluminum and we're going to put it in the middle of our diagram. Here's aluminum right in the middle of my diagram. And now we are going to fully bond it to our Cl3. So we need 3 bonds, 1, 2, 3, 1, 2, 3. And now we're going to fully fill it with chlorines. And we are going to fully fill chlorine's valence electrons. So we are going to fill it. This is the rule of octet. Every atom wants to fill this rule of octet except hydrogen and helium. They can only form 1 bond. So here is my drawing. Now I'm going to count how many valence electrons to make sure it is satisfied. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I am currently all set. There is no issues here. Aluminum can only form 3 bonds. And yeah, so now we are going to look at formal charge. So the formal charge is the number of valence electrons minus the number of non-bonding minus the number of bonds. So we're going to do the FC. That's a good representation, like shorthand for formal charge, FC, of Al, which is aluminum. So we're going to take the number of valence electrons in aluminum, 3, minus the number of non-bonding. So the number of non-bonding is 0, and there are 3 bonds. Oh, sorry, should be a plus. And we're going to get 3 minus 3, which is 0, meaning aluminum has no charge in the molecule. So next we are going to do the formal charge for chlorine, which chlorine is the same all throughout. There's no different chlorine. They all look the same. So we are going to take 7, which is the number of valence electrons, and subtract the number of non-bonding, which is 6, plus the number of bonds, which is 1. 7 minus 7 equals 0. So we are currently looking at the Lewis structure for aluminum chloride, and something I like to do to help me out later is say that the number of bonds is 3. There are 3 bonds and there are 0 non-bonds on the central atom. This will help me later on when I am doing my electron domain geometry. So moving on, I'm just going to grab my eraser and I'm going to get rid of the formal charge. So here it is. The formal charge is 0 and 0. So next we're going to talk about electron domains. There are currently 3. You can tell because there are 3 bonds on aluminum. So we are going to say that the electron domain equals 3. And now that we know how many electron domains, we can find the electron domain geometry, which again is trigonoplanar. And now looking at the number of non-bonding, we can find the molecular geometry. Whoop, I dropped my pen. The molecular geometry equals trigonoplanar as well, because there are no lone pairs that would change the shape. Okay, so that's our second example all done of aluminum chloride. So next we are going to move on to a little bit harder molecules. So the next molecule we will be looking at is called xenon tetrafluoride. So xenon tetrafluoride looks like this. I know what you're thinking. You may be like, hey, but xenon's a noble gas. It shouldn't bond with anything. But xenon is just slightly reactive. Like, it has a slight charge that sometimes likes to show up and mess things up. So, but in this case, it likes to bond with fluorine. So we are going to do the number of valence electrons for this example. So we are going to start with xenon. Xenon has 8 valence electrons. Then we are going to add in the number of fluorine valence electrons, which is 7. But there are 4 fluorines, so we need to multiply it by 4. So 7 times 4 is 28. 28 plus 8 is 36. So we're going to have 36 valence electrons, which is more than the last 2 examples, because the last 2 examples had 24 valence electrons. So now we're working with 36 valence electrons. So we're going to start by drawing our most unique atom, which in this case is xenon. Xenon is the most unique because there are 4 fluorines. Therefore, that is not unique. So we're going to draw xenon in the middle. Now we are going to draw our 4 bonds. 1, 2, 3, 4. Now we are going to fill it with fluorine. So we're going to go 1 fluorine, 2 fluorine, 3 fluorine, 4 fluorine. Okay. Now we're going to fill fluorine's valence electrons. So we get 8. So this counts for 2, remember? So we're going to fill with 3 sets of lone pairs. This is an important step because it's very important to make sure every molecule achieves the octet. Okay, we are now going to count how many valence electrons we have to see if we satisfy the 36. So we're going to go 8, 8, 8, 8. So that would be 32. We are 4 electrons short from our 36. Now you might be like, but there's nowhere else to fill. We're currently all filled. What do we do now? So what we do now is we look at our periodic table. If we look at our periodic table from period 3 and down, we are going to be able to overfill the octet. They can fill their electron shells more than 8. So xenon happens to be able to fit 4 more electrons around the central atom. So we're going to do 2 sets of lone pairs. 1, 2 sets of lone pairs. And this is what our Lewis dot diagram structure is going to look like. Now we will move on to see how many bonds and how many non-bonding. Remember how I told you this is important? This is why. So we're going to put the number of bonds, which is 4, and the number of non-bonds is 2. So looking at this, we are going to move on to formal charge. Formal charge, okay. So the formal charge of this whole atom should equal 0 because it has no charge. We will see later on what happens when there is a formal charge, and we will figure out how to work through that. But baby steps, baby steps. We are going to work with this first. So we're going to take fluorine first, because there are more of them. I just like to start with which ones there's more of. So there are 7 valence electrons, and we're going to subtract the amount of non-bonding, which is 6, and add in the bond. So 7 minus 7 is 0. Next, we are going to do the formal charge of xenon. Xenon has 8 valence electrons, and we're going to subtract the 4 bonds plus the 4 non-bonding. This is 8 minus 8, which equals 0, meaning there is no formal charge on xenon. Okay, I'm just going to get rid of this formal charge and this period 3 right here. Okay, next we are going to look at the electron domains. Now this is where it gets tricky because the electron domain geometry and the molecular geometry are 2 different things this time. So, for our electron domains, we have 6. Can everybody see why we have 6? We have 6 because we have 1, 2, 3, 4, 5, 6. The electron pairs, the pairs of lone pairs, those count towards the electron domain geometry. So now that we can see the 2 sets of lone pairs, we are going to add it in. So our electron domains, we have 6. So our electron domain geometry is octahedral, meaning that there are 6 electron domains. Okay, now because of these 2 sets of lone pairs, it will not be an octahedral shape. Like as we draw the shape, it will not be an octahedral, which means that you have 6 different bonds going 6 different places. It will be a square planar. So, the molecular geometry is a square planar. Now you may ask, how do we draw this? How does this look? Well, we can draw this by starting the same way we normally do. We're going to start with xenon right in the middle. We have xenon. Now, I like to start by drawing the lone pairs because I know that's what's going to mess me up. So I'm going to put the 2 sets of lone pairs at the top and the bottom of the central atom, like this. Something I really like to do that's important because it shows that there's structure that can mess you up is you're going to put them in lobes. These little lobes, sometimes they look like little aliens in my opinion, but these are called lobes, these little circles around the central atom. Now, what are we going to do with all of these fluorines? Where are they going to go? You put 2 things on the top and bottom. What do we do now? Well, these are going to be 3-dimensional. octahedral objects are three-dimensional. It can't lay flat on paper. You can't correctly draw it on paper. So this is how we draw it on paper. We are going to make these things called wedges. They are these little triangle-shaped things, and we are going to add a fluorine onto it. And we are going to do another one. This means it's coming off of the board. It's coming into that space. There, that satisfies 2 of our fluorines. Now we are going to draw fluorines that are going into the board. Into the board, like dashes into the board, wedges out of the board. So we are going to fill our fluorines again. And now the last step is we're going to fill all of our valence electrons on the fluorines. So that means 6 lone pair electrons. Okay, so this is our final drawing of our molecular geometries. Okay. Our last example for the day is going to be phosphite. This has a charge. It's very similar to phosphate, except it has 3 oxygens instead of 4. So we are going to look at phosphite, which is PO3. PO3 is phosphite, and this has a -3 charge, which means we need to be very, very cautious about where our charges go. We need to remember our charges exist. So, to find the valence electrons, we are going to take the amount on phosphorus, which are 5. We're going to add in the amount of oxygen, which is 6, but we have 3, so we got to multiply by 3. And now when we have a charge, and especially a negative charge, what we are going to do is we are going to add 3 more valence electrons. So we're going to add the charge. If this was positive, we'd subtract. Okay, so it's the opposite. So negative add, positive subtract. Super weird, I know, that's just, I didn't make the rules. So, we are going to have 8 plus 18, which is 26 valence electrons. Okay, now we are going to find the most unique atom, which would be the phosphorus. So that is going to be our central atom. So we're going to start by writing our P in the middle. Okay, now we are going to fully bond all of our oxygens on. So we're going to go 1, 2, 3, and we're going to draw in our oxygens. So we have 3 oxygens, so we're going to draw in 3 oxygens. So next we're going to fully fill the octet of all of the oxygens. Now that we have fully filled in the amount of electrons onto the oxygens, we need to look at this phosphorus atom right here. This phosphorus atom can make 4 bonds. So what we're missing is a set of lone pairs. So this is a lone pair right here. This is how you draw it. And this is the molecule we are currently looking at right now. So this is how you draw the Lewis structure. Now on to the important part, the formal charge. So the formal charge of phosphorus, we're going to start with phosphorus, okay? Phosphorus has 5 valence electrons. And we're going to subtract the number of non-bonding, which is 2, plus the number of bonds, which is 3. 5 minus 5 equals 0. So the phosphorus isn't what's charged on this atom. So it must be this molecule. So it must be the oxygen. Let's look at oxygen. Oxygen has 6 valence electrons. We're going to subtract the 6 non-bonding plus the 1 bond. This would be 7. 6 minus 7 is -1. Now you might say, hey, it's only a -1 charge. How did they get the -3 charge for the whole molecule? Well, there are 3 oxygen atoms on this molecule. So this one's -1, this one's -1, and this one's -1, making the whole molecule -3 charge. This is really important to put these 2 brackets and your charge to let everybody know that this is a charged molecule. Okay, now for our last step, we are going to look at the molecular geometry. So, how many electron domains are there? There are 4 electron domains. 1, 2, 3, 4. So there are 4 EDs, meaning that this is a tetrahedral electron domain geometry. Okay, but this set of lone pairs, excuse me, this set of lone pairs causes it to push down on these 3 and make it a molecular geometry of trigonal pyramidal, meaning it is again 3D in shape and cannot lie flat on the paper. Like the last example we looked at was 3 other atoms bonding to the central atom was a trigonal planar that laid flat on paper. So if you can imagine that trigonal planar laying on paper that has something pulling it up a little bit, it looks like a pyramid. And yeah, it's due to the lone pairs causing it to push down and causing the bond angle to change. So, in order to draw the molecular geometry of phosphite, we are going to start with phosphorus being my central atom. Now, we are going to draw the lone pairs at the top. You could also draw them at the bottom. I just prefer to draw them at the top. We're going to put them in a lobe. A little alien. It's not an alien though. It is phosphorus with lone pairs. Now we are going to have one that remains on this plane, which is oxygen. And then we are going to have one that goes into the board. So we're going to draw a wedge, that comes out of the board. So we're going to draw a wedge and then goes into the board. So we're going to draw dashes. And now we are going to fill the octet of oxygen. Now, the most important step after you do this is to make sure you put brackets around it and you put that it's -3 charged. Okay, thank you guys so much for coming to my lesson today. I really appreciate it, and I hope you all have a great day.